that the curl and what?
Divergence is 0.
Not necessarily. Look, if you take the div of this, look at the div. Here's our vector field. Remember, div is like partial of this with respect to x plus partial of this with respect to y, partial of this with respect to z. Oh, wait, well, hold on. This one you get 1 minus 1. You get 0. Curl. I don't know. We could check it, but seems like it would make sense that way.
Yeah, that makes sense. Flux doesn't.
All right, let's do another one. This one I'm trying to move a little faster, but I need you to let me know if you're just sitting there going, I just got to get through to next Tuesday. I mean, I want you to understand this, you know. This is like we've reached the end here, but it's a good end. It's like bringing this all together into some pretty cool stuff. All right, look at this object. You have a surface, let's see, you've got, looks like one of those like aircraft hangars, right? All right, so we want to find the flux on this entire surface, S. S is the boundary of the solid half of the cylinder. Z is between 0 and root 1 minus y squared. That draws me basically this and everything inside. And then our x's are stuck between 0 and 2. So the back side of this is x is 0. The front side of this is x is 2. Understand? So two planes, the cylinder, and then we also have the bottom. So let's label these surfaces. I'm going to call this one right here S1. The one in the back side there, let's call that S2. How about the one that's underneath right there, S3? And this one right here, let's call it S4. That sound good to you? All right, what can you tell me about S1? It's the face, it's on a plane, right? What's the plane that lives on? X is 2. X is 2, because our x values, x is coming out at us, okay, everyone? So x is 2 is this one. So if I'm going to try and find the flux through that surface, maybe I can do the same thing I just did in the previous example. When we had that flat surface like that, can you tell me about the normal vectors for that S1? If this is positively oriented, meaning normals go out of the solid. What are they? All the normals that come out of this, no matter where you pick, what do they all have common? What are they? 1, 0, 0, right? The normal, so I'm going to write this, the normal vectors for this surface 1 all have this in common. They're all 1, 0, 0. And that means that if I want to find the flux here over S1 of the vector field dotted ds, I could just do this f dot n ds. This one I'll write out. This is double integral over S1 of, what's my vector field here? X squared, y squared, z squared. Dot that with 1, 0, 0 ds. And what does that become when you dot it? X squared. So still have this surface integral, x squared ds. And because we are actually on this surface, right, on this plane, the x value is always what? 0. So we're just trying to do a surface integral of 0, which is 0. X is, oh, sorry, yes. We were doing S1. Why? I said 2, didn't I? I said 2 and I wrote 0 down. Why didn't y'all tell me something earlier? Okay, that was S2, right, that I was doing there? Say again, yes? This should be what then?
So
4. Go ahead.
the normal vector.
Yes.
Coming out. Could you tell me how it's going to be 1, 0, 0?
Okay.
So it has to do with the plane, but
It's I hat. It's I hat.
so just because of that. Okay.
Right? If I have, I don't know. It's a uninormal vector, yes. That's why it's 1, yes. So you have, x, y, z like this. X, y, z, right, is back there. So this x-axis comes out in the same direction as these blue vectors. So what's a vector that's pointing in the same direction with unit length? That's I hat. That's 1, 0, 0.
Yeah, I was just like.
Well, it's a good question, because if you have that question, I'm sure someone else does. All right? Okay, so sorry about that x is 0. I was ahead of myself, I guess. That should be a 2, which means when we square it, we get 4, and then we can pull the 4 out. And that's now 1 in there, and this just means surface area of S1, which we should be able to find just by looking, right? S1, if we look at it this way, right, what's the radius? How far out is this? What's the distance from here to here? Well, that comes from this equation, right? Comes from that. That's where it's coming from. So to get a z value of 0, you have to plug 1 in, or negative 1. So 1 and negative 1? Yes or no? I could turn it. I'm going to mess up all my stuff, though. Turn it that way. You can kind of see it that way a little bit. Yes? Yeah? All right, so negative 1, 1, and that's my y value. But it doesn't matter. We know that the radius is 1, right? So the area of an entire circle would be pi r squared. Since r is 1, this would just be pi, but we're taking half of it. So it's 4 times half of the area, which is going to be just 2 pi. Okay? Now, let's do S2. S2 is going to be the one that I almost did a second ago. What's the only thing that changes with S2? That becomes 2. That becomes 0. I'm using the same normal vector, right? Because, well, am I using the same normal vector? Hold on. It should point the other direction because they're coming out the back side. You can't really see them. They're back there, and they're pointed out that way on the back side. So they should be what? Negative 1, 0, 0. And then when we go through here, we change this to S2. Change this to S2, change this to S2, change this to negative, change this to S2, and this actually, when we dot it, gave us a negative x squared. But that doesn't matter, because at the next step, x is 0, so we just get 0. Questions on that? Okay, so what about S3? What can you tell me about S3 if it's the bottom of this hanger? It's a rectangle, right? What can you tell me? I mean, like this one was, we said this was part of a plane, x equals 2. The back one was x equals 0. The bottom one we could say is z is 0, right? So why don't we do that? We're going to say the bottom, S3, has the equation z equals 0. How about a normal vector for that surface? 0, 0, negative 1, because your normal vectors will be pointing out straight downward, right, off the bottom of that surface. So that would be negative k, k hat. Agreed? This is all still the same. I'm going to dot here, but then this vector changes. And it changes to 0, 0, negative 1. Am I moving too quick, filling in the blanks here like this? Am I? I can slow down.
It takes a little while to.
I understand.
Because we can't really just erase it.
I understand. I know that. That's why I'm asking. I can slow down.
That's all good. So-
You're okay? I also am taking into account the fact that this is on video. You know, can always be played back. So, all right, S3. So tell me about this dot product here. What do you get when you dot product that? You get negative z squared. ds, and z is 0. Yeah, so this is going to zero out again. So we have no contribution to the flux through the bottom of the surface. Yes?
If we needed a negative vector on the y-axis, would it be positive as negative j?
Wait, say again. If we needed what?
A negative vector.
Uh-huh. On the y-axis,
Yeah. So since you use j,
it would be negative j. Yeah.
would that make it positive?
Would that make it positive? I'm not quite sure I follow you.
Like for z, it was negative 1.
Uh-huh.
So for a negative y, it didn't need to be negative 1, but since we need to put a minus sign for j.
Why am I going to put a minus sign for j?
I'm just curious.
No. J hat is defined to be 0, negative 1, 0. Negative j hat would be that. J hat would just be 0, 1, 0.
Okay, so that's just the top one's just a cross product.
This is just negative j hat. I'm still not following. It's just for cross product? What?
The switching signs and the cross
Okay, I think I understand. When you do your cross product, the middle one always has to switch signs. That's what you're referring to? Okay. All right, we've got 3 of the 4 surfaces. Now, S4 is the most challenging because it's not flat. So the normal vector is not always constant. Do y'all see that? That's kind of like when we see flat surfaces, we like it because the normal is always going to stay the same. But once we start moving around something that has curve to it, it's going to change. So this formula is not as nice. So we'll just go back to the other method. Can you look at S4 in the shortcut, as a shortcut? Can you look at the surface as being a function of 2 variables? Okay? And it's the z, right? The z is a function of which 2 variables? So what's the equation? Sorry. Square root of 1 minus y squared. And of course, our y here is going to be between negative 1 and 1. That's what it took to draw it, right? But that would draw me the surface, wouldn't it? That would draw me the surface. And so I'm going to say that this is a function g of xy is this. And that's the thing I'll be taking partials of. And then I'm going to go and I'll label this is of course my P, my Q, and my R. So I'm doing just what I did the previous example. And which formula am I going to use here? Top one? Right? Top one. My normals are pointed upward. Well, do you agree that if I draw normals coming off of this green thing, that the z component is always positive? Right? I've got a little bit of a tilt upward on all of these. If I was on the bottom side, then I would start to get negative z components. But all these vectors should have positive z components. All right, well, let's go ahead and use the formula then. This becomes, let's see, flux over S4 should become the double integral over d, where d is going to be the restrictions on x and y that draw me this surface. And can you already see what the restrictions on x and y are going to be to draw just this top part? What's the projection of that surface onto the ground? It's a rectangle, so it's going to be a pretty straightforward limits of integration, right? And I'm going to be doing here negative p, which is negative x squared, times the partial of g with respect to x, 0, there is no x in there, okay, minus q minus y squared times, bless you, the partial of g with respect to y. Now that is going to take a little bit of work. The partial of g with respect to y. So if you took derivative of this with respect to y, did some chain rule, you should get negative y over square root of 1 minus y squared. You trust me that that would be that, right? And then finishing off the formula, plus r, so plus z squared dA. And I'll clean that up. Pardon me? But when you took the derivative of the root, it was 1/2, so I already took care of that. Okay, I'm going to just write this down again. This is going to be double integral over d. This is gone. This becomes what, like negative y cubed over square root of 1 minus y squared? Yeah, negative is plus. I'm checking out, man. I'm checking out. Plus z squared. Now look, what are the integration variables going to be here? X and y, right? So we can't have a z in here. But do we know what z squared is? Well, that's what z is, right? So square both sides. So z squared is 1 minus y squared. So I'm going to replace this with 1 minus y squared plus 1 minus y squared. And then dA. And I think that's good. I'm ready to go ahead and get my limits of integration. I just want to look at this region on the ground, right? The projection of that green surface onto the ground should create, now just be careful here. This is x, this is y. Remember, x is coming out at you, right? So my x is going to go out to 2. And my y is actually this part left and right. So negative 1, 1. That. So my restrictions are x is between 0 and 2, y is between negative 1 and 1. So last step I'm going to do is to set up my limits of integration, 0 to 2, negative 1 to 1, of y cubed over square root of 1 minus y squared plus 1 minus y squared dy dx, because I chose the order here to be like this. And if you do this, which I'm not going to do, this one is kind of an interesting integral right here. It's a little interesting. If I were doing that, I would do a u substitution, let u be equal to 1 minus y squared. And I would split my numerator up into y squared times y, and it will work out real nice that way. Another way you could do it is by using trig substitution, but that takes a lot longer. This is a lot cleaner to do it that way. But at the end of the day here, if you do this integral, you get 8/3. So the final result